Now the very next thing that I'd like to do is work an example, a long example start to finish, of finding the Taylor series for a particular function. But before we get into that intense computation, I wanted to give you a little bit of funny about Taylor series. So nothing interesting to say here, just something fun. Here's the example I'd like to work in full detail. And it can be computationally intense, but the nice thing about Taylor or Maclaurin series is that the process of solving them is very straightforward and rote in terms of computation. So I'd like to give you an example of how that's done. So for our example, we'll be computing the Taylor series for the function f of x is equal to the natural log of x, and we're going to center this Taylor series at a is equal to 1. Whenever I am computing a Taylor series, I make myself a little chart like you see over here on the left, where I list my different n values. What I'm going to put into this column is the nth derivative of the function generically as a function of x. And then what I'm going to put into this column over here are the values of that derivative evaluated at the center of our series. And the reason I'm doing that is because the values in this column are the numerator of this coefficient on the terms of our Taylor series. So let's get started. When I don't take any derivatives of my function, the function I have in this specific case is the natural log of x. In this column, I put the value of the natural log of my center. My center is 1, and the natural log of 1 is 0. So very uneventfully, the first term in the Taylor series for natural log of x centered at 1 is 0. Okay, now let's actually compute some derivatives. The derivative of the natural log of x is 1 over x. I'm going to rewrite that as x to the negative first power because that's going to be easier for taking derivatives as I continue on down this column. When I take that 1 over x function and plug a is equal to 1 in for the x value, I get 1 over 1, or just 1. In the next term of my Taylor series, I take that value of 1 and plug it into my numerator. The denominator of the coefficient becomes 1 factorial, and I put an x minus 1 to the first power here, and then I bounce back to my table. So taking the second derivative of my function, or in other words, the derivative of the thing right above me in this column, I get a negative x to the negative 2 power, and when I plug in a value of 1 for x, what I end up getting is just the number negative 1. So when I come back to my formula, I plug negative 1 into the numerator. I'm on to an n value of 2, so my denominator becomes a 2 factorial, and the x minus 1 should be raised to the second power, and I move back. Taking the third derivative of my natural log of x function, or in other words, the derivative of the thing that came right above me, I bring down the negative 2, my two minus signs cancel, and what I end up with is a coefficient of 2 on my x to the negative third power here. So I can think of that as a 2 over x cubed if I'd like, so that when I plug in 1 for that x value, thought of as a denominator of a fraction, the numerical value I get is 2 times 1. Returning to my Taylor series, I put a value of 2 times 1 in the numerator. My n is equal to 3 now, so I have a 3 factorial in the denominator of this coefficient, and then I have an x minus 1 cubed term. Let's return to our table one more time to hopefully start to see a pattern for what's going on here, because that's the purpose of the table, is to help us see and understand patterns so we can ultimately stop this process and generalize. At the next stage, I'm going to bring down that 3 value, and the coefficient on my x will be negative, and it will be 3 times 2 times 1, or 3 factorial. And then I'll have an x to the negative 4th power. When I move from this column to this column, I prefer to think of that x to the negative 4th power as being an x to the 4th in the denominator of a fraction. But when I plug in 1, that whole denominator just goes away, and the coefficient I'm getting when n is equal to 4 is a 3 factorial, but with a minus sign. Plugging that into my Taylor series formula, I end up with a negative 3 factorial over 4 factorial times x minus 1 to the 4th power. And here I start to see my patterns. When n is equal to 1, I've got a 0 factorial over a 1 factorial. When n is equal to 2, my coefficient has a negative sign, and then it's a 1 factorial over a 2 factorial. When n is equal to 3, my coefficient is a 2 factorial over a 3 factorial. When n is equal to 4, my coefficient has a minus sign and is a 3 factorial over a 4 factorial. And I start to notice a pattern for what this value is going to be for an arbitrary n. At stage n, what we were finding is that we had an x to the negative n power for our derivative, and then the coefficient on that x to the negative n was one number smaller, factorial. We also noticed an alternating behavior, so we have an alternator right here. What we need to be cautious of with this alternator, it's very tempting to write something like negative 1 to the n, as that's our general form for an alternator, but we need the alternator to match up with when our derivatives are actually negative versus positive. So if you'll take a look at our previous slide, negative 1 to the n, that generic alternator, is going to be a positive 1 when n is even, and a negative 1 when n is odd. We have the opposite of that behavior. We have positive values when n is odd, in the 1 and the 3 cases, and we have negative values when n is even. So what we want to do is actually take that negative 1 to the n alternator and multiply it by negative 1 in order to switch those signs. Or in other words, we can just use this alternator, negative 1 to the n plus 1 here. So this is a formula for our general nth derivative of the natural log of x with x's in place. But as we saw, when we plug in a 1 value for this x, that term goes away. And when we evaluate this derivative at 1, we simply get this expression. Next, we can directly return to our Taylor series formula, and where we had that nth derivative of the function evaluated at a, we'll substitute in this formula right there, and everything else stays exactly the same. Do notice that because our first term was 0, and our pattern for derivatives doesn't really apply to the natural log of x until we've actually taken one derivative, we've changed the sum from starting at 0 to starting at 1. Next, let's see if we can simplify one step further. Instead of n factorial in that denominator, let's think of n factorial, as we've done with factorials before, as n times n minus 1 factorial. When we do that, these values cancel, and we're left with our final answer, which is that a Taylor series representation for f of x is equal to the natural log of x, centered at a is equal to 1, can be given by this beautiful series.